In this video, we'll go over worksheets 3 and 4 that covered chapters 3 through chapter 5. So, looking at the first problem, these first few problems were on probability. Asking a probability of drawing an ace if you just draw one card from the deck. So remember that there are a total of 4 aces. So you have 4 events that we're looking for out of the total of 52 cards, and that reduces to 1 out of 13 if you divide the numerator and denominator by 4. Second one, using the fundamental counting principle for license plates that have 3 letters followed by 3 digits. So if you imagine the 6 characters like this, you just write down the number of choices you have for each of those characters. So the 3 letters, you have 26 choices for each of them. There's no restriction on repetition or anything like that. And then 3 digits, there's 10 digits in total. So you have 10 options for each of those. And then the fundamental counting principle says you multiply all these numbers together. So that comes out to be the 17 million possible license plates. Next, we're asked the probability that a student owns a credit card given that they're a freshman. So remember, when looking at a table like this, the given part kind of tells you what to focus on. So all the numbers will come from this row of freshmen. And then of those 60 freshmen, 22 own a credit card. So it'll be 22 out of the total of 60. And that came out to be about this 37%. Next, multiple choice test has 5 questions, each with 5 choices for the answer. And of course, only one of those choices is correct. If you decide to randomly guess, what's the probability that you get the first 2 questions correctly? So this would be 2 independent events, answering the first question followed by answering the second question. And the probability for each is the same. It's 1/5. So the multiplication rule tells us that you would take that 1/5 for the first question, probability of getting the first question right, and multiply it by another 1/5, probability of getting the second question right. That comes out to 1 out of 25, or about a 4% chance, and you ended up getting both of them right. Next, looking at events, whether or not they're mutually exclusive. So the first example, getting a 7 or getting a jack. So the question you want to ask yourself is, can these 2 happen at the same time? Or is there a card that is both a 7 and a jack? In this case, that can't happen at the same time, so they are mutually exclusive. And the next one, club and king. These can happen at the same time. There is a king of clubs, so these are not mutually exclusive. Finally, for this page, we're looking for the probability that a card drawn is an ace or a heart. So using the word or here, we use the formula for or, which is the addition formula. So the probability that you get an ace plus the probability that you have a heart. And that would be the end of it if they were mutually exclusive. But they are not mutually exclusive. You have the ace of hearts that is both. So you'd subtract the probability of getting an ace and a heart. So that would be, well, let's put it underneath. So the probability of an ace, we saw that before. That was 4 out of 52, the 4 aces out of the 52. For hearts, there's a total of 13 hearts, 13 of any suit. And we have to subtract the 1 ace of hearts that we're double counting by adding those together. So that one came out to be 16 out of 52, but that reduces to 4 out of 13. So, next page. Here, another OR problem. The probability that we select someone at random and give someone that's a regular smoker or a heavy smoker. So there's a total of 87 regular smokers, and there's a total of 11 heavy smokers, and a grand total of 420 people, or students. So the probability of regular would be the 87 out of 420, and the probability of heavy would be the 11 out of the 420. And this already has a common denominator, so we just add together. And we don't have to subtract anything, because these are separate columns. That's one way to tell that they're mutually exclusive, but also just logically you can't be regular and heavy smoker at the same time. So this comes out to be 98 out of 420, which if you put in the calculator, we get about a 23% chance. Next, this starts into chapter 4, looking at probability distributions. So here we have X representing the number of patients entering the hospital and the probabilities of each of those occurrences happening. And so to find mean and standard deviation, one thing you could do is put these into two columns in the calculator. So that's list 1 and list 2. And then if you run the one variable stats with list 1 and list 2, that will tell you what the mean and standard deviation is. In this case, it was C. You can also use the formulas, but I won't do that in this video because that takes some time. I will do, like for the next example, I'll do formula for the mean, but the formula for standard deviation is kind of long. So I think this would be easier here. For the raffle, each ticket sold at $10. And I'll go ahead and make a table over here of the events. So this is X, the events, and the probability of each event. So you have 3 possible prizes, but don't forget that you spent $10 to possibly get those prizes. So your net gain will be 10 less in each case. So $47.90 for if you win this first prize, $11.90 if you win the second one, and then $3.90 if you win the third. But of course there's one other event here, which is the most likely thing to happen, is just you don't win anything at all. So you just lose your $10. So those are the 4 events, or 4 outcomes. And then the probability for each, well, each of these is just 1 out of 10,000. And the losing, well, you have 3 winning tickets, so you have 9,997 losing tickets. So it would be that out of 10,000. And for the mean, you just multiply straight across and then add all that together. So here you should have ended up with a negative $9.36 as the expected value of that ticket. Next, we start looking at the binomial experiments. We have a test with 30 multiple choice questions, 5 possible answers. Each one just has 1 correct. And we want the mean and standard deviation of the number of correct answers. So we can think of this as a binomial experiment because each question would be an experiment. You randomly guess it, and you have 2 possibilities. You either get it right or wrong. The probability of getting it right, so the P here, is 1 out of 5. The number of trials, number of times you repeat this experiment, is for each of the questions, so n is 30. And for standard deviation we need q, so q is the probability of getting a question wrong, which is 4 out of 5. The more likely thing to happen if you're guessing. And so recall the formulas. The mean in a binomial experiment is NP, so just multiply those together. Oh, can't see that. And then the standard deviation was the square root of NPQ. Oops, NPQ. Sorry, that didn't come out that great. And so you just plug into each of these formulas. The first one, I guess, might be obvious or the easiest to explain. If you guessed on all 30 with a 1/5 chance of getting any one of them right, then you'd expect to get 1/5 of them right, which is 6. And then standard deviation, you'd have to use the formula here. So that came out to be B. So So a mean of 6, standard deviation of about 2. Next one, the probability of getting 2 boys out of the 10 births. So this is another probability experiment, because again you have 2 outcomes, male or female, and you have a total of 10 births, so n, the number of trials is 10. The probability of getting a boy, the same as getting a girl, is 1/2. And what else we need here, we want exactly 2 boys, so that's our number of successes, so x is 2. And for this we use the binomial formula. You could use the formula if you want, but I think it's easier in the calculator, especially for the next ones. Do the binomial PDF, and that's when you see the word exactly, you use the binomial PDF. And so you plug all that in and it gives you the answer. So that one was B, about a 4% chance of getting exactly 2 of the 10 births as boys. Next, the probability that a woman in this age range is never married is 40%, so that's our probability of success, 0.4. Survey of 10 women, so that's our n, is 10. And the probability that 2 or fewer is never married is related to our x. I guess we can say that x is 2 here, because 2 or fewer is up to 2. So if you think of what the word cumulative means, this would be up the cumulative probability up to 2. So that's where we use the binomial CDF. And I forgot to write it here, but you put n, p, and x. So let's put that there. So 10, 1/2, and 2. In the CDF, you do, again, npx, so 10.4, and whatever you're going up to. So in this case, it is 2. So that came out to be C, about a 17% chance of this happening. But when you go the other way, so this was 2 or fewer, that's kind of the easier one, or the one that the binomial CDF is designed for. But if you want greater than some value, or at least some value, like what we're going to see in the next one, at least 6, we have to do something a little bit different. So 70% wear glasses for driving. So that would be a P, probability of success of 0.7. 10 adults again, so our n is 10 once again. And for x, we have to be careful. The at least 6, the opposite of that, put opposite here, would be, 5 or fewer. So to sort of make it match the previous problem of 2 or fewer. So that makes our x 5. So be careful there. So if I do binomial, or binom CDF with these numbers in 5, so 10, 0.7, and 5, that will give me the 5 or fewer, which is the opposite of what I want. So I need to subtract that from 1 to get the at least 6. So that one came out to be about an 85% chance that that happens. Okay, let's take a look at our next worksheet. This one covered chapter 5. First, looking at finding areas under the normal curve. So area to the right, remember if you were to look this up in the table, you would get the area to the left. So if you look it up and get that area, you'd have to subtract from 1 to get the area to the right. So, well, knowing what the answer is, this must have been 0.0968, I suppose, because that's the opposite of the answer, or 1 minus the answer. So if you look that up, you should get that, and then you do 1 minus it, and you get the area to the right, which is what we really want here. The area in between, I'll show you the other way that we use with the calculator. And the calculator is sort of the most natural one to do for area in between. You use the normal CDF in the calculator. And then you just put the two values in, so 0.45 or negative 0.45 up to 2.11. This is definitely not to scale, like 2.11 would be much further out, or look closer to the tail like this, but that's okay. So this one came out to be A. If you use the table here, you could look up both numbers, you get areas for each, and then you just subtract them. That will also give you A. So here we're told about a normal distribution of suitcases with a mean of 15.5, standard deviation of 3.6, which is the same in the next problem as well. We want to find the probability that they'll lose less than 20 suitcases. So let's draw a picture of what that looks like. So the mean of 15.5, standard deviation of 3.6. So 20 would be maybe around here, considering that standard deviation of 3.6. So losing less than that would be the area to the left. So doing this, I think helps in getting an idea of what kind of answer we're expecting here. So we're expecting certainly something quite a bit bigger than 50%, judging by the picture, even though my picture may not be perfect. It definitely eliminates some things. It actually probably eliminates it completely down to B. So that's nice in this problem. But you would first get a z-score for the 20, because if I were to get a z-score and look that up, I would get the area to the left. So you do z as 20 minus 15.5 over the standard deviation 3.6, just using the z-score formula. I don't have it written down, but that would give you the z-score here. And then you would look that up, and that would give you B. Next one's a similar idea between 10 and 20. So same picture, but let's just change it slightly, where we put 10 on here now. And so now we want this area in between. And so we would need a z-score also for 10. So if we get a z-score for 10, same process, 10 minus the mean divided by standard deviation. That would give us that z-score, and then you could use normal CDF like we did up here, or you could look up both z-scores in the z-score table and subtract the areas. So in this case, you should have gotten C. It's about 83%. So it doesn't knock out that much if you sort of compare these two. It knocks out about 6%. Okay. Next, we're looking at salaries of elementary school teachers. Mean of 32,000, standard deviation of 3,000. So if we select a teacher at random, what's the probability that they make more than 36,000? So again, drawing a picture is a good idea. So we put the mean of 32,000 in the middle, and then we kind of locate where 36,000 would be in terms of the standard deviation. So one standard deviation away would be like 35,000, so it's a little bit more than that, maybe about there. And then it's more than 36,000, so we want the area to the right. So once again, find a z-score for the 36,000 by using the z-score formula. This one I can actually do in my head. You get like a 1.33. So if you look that up, you would get the opposite of what we want, because that would be area to the left. But if you do 1 minus that, you would get what we actually want, which is this one. So I believe if you look it up, you'd get that one. If you look up 1.33, but then you do 1 minus that, so you get that one. Next, we want a z-score with 70% of the distribution on its right. So this is 5.3, where we work backwards. So we can draw a picture of what that would look like. So imagine this, you want 70% to be on the right. So that means the z-score would have to be over here somewhere. And then this area here would be the 70%, or 0.7. So here, to use either the z-score table or the inverse norm function in the calculator, you need the area to the left. So you subtract from 1, you get 0.3 as the area to the left. And then you can do, in the calculator, you do inverse norm of 0.3. This is what I recommend because you're not going to find 0.3 in the z-score table exactly. You'll have to find something closest to it and then trace back to get a z-score. But inverse norm is definitely easier here. Just put in that 0.3, the area to the left, and this time we get B. We did expect a negative z-score, so I guess they're all negative, so you can't eliminate in this problem. And the next one here, 98% in the center. Let's draw our distribution. So this one might be one of the more tricky ones. We need two z-scores here, where this area is 98%. Shade that. Well, again, we need to work with the area to the left of one of these z-scores. So one we could pick on is this one, because we could figure out what the area to the left is there, because the remaining 2% is split evenly among the two tails. So you have 1% here, and in particular you have 1% here, or 0.01 as the area. So that's what you have to work with. You could do inverse norm of 0.01, or again, try and look it up in the z-score table to find it. That should give you negative 2.33. And because it's symmetric, the other z-score would be positive 2.33. But you could figure out that area too, because it would be the 98 plus the 1%, so it would be 0.99. Inverse norm of that should give you the 2.33. Okay. Finish up with the other side. Once again, with the salaries of elementary school teachers, this time has a mean of 29,000, standard deviation of 5,000. So what's the cutoff salary for teachers in the bottom 1%? So let's draw a picture of that. So a mean of 29,000, standard deviation of 5,000, but that doesn't really matter here. We're just going to figure out what the bottom 1% would look like, or 10%. And so that would be an area of 0.1. So we could get a z-score for that, of course. We could do inverse norm of 0.1. Yeah, I don't have that z-score, but you would use the formula that converts back to a data value. That was x equals mu plus standard deviation times the z-score that you have. I think it was probably written the other way around, but that's fine. So whatever z-score you get from that, just plug in there, plug in the mean and standard deviation. That should give you B. I mean, that makes sense, right? It has to be less than the 29,000. So these are the only two that made sense. The other two could be eliminated. Okay. Here we have scores on a math exam had a mean of 78, standard deviation of 8. And we want to know what x value corresponds to a z-score of minus 1.26. So interpreting that, that would be about 1 1/4 standard deviations lower than the mean. So we already have a z-score, so we don't have to do the first step that we did up here. We just need to do the second step, converting it to an x value. So we put in the mean of 78, we add the standard deviation of 8, and then plug in the z-score minus 1.28. So that gives you a score of let's see here, C, 67.8. Again, only a couple of the, well, this is the only one you could truly eliminate. The rest of them are smaller than the mean, and you expected it to be smaller than the mean because the z-score was negative. Okay, next, this starts into 5.4, the last section, because we're told a mean and standard deviation for length of pregnancies, But now instead of having an individual that we're selecting, we're looking at a group that's being selected, or a sample of women that are selected, and looking at the probability that their mean pregnancy is in a certain range. So we can still draw a picture, of course. So the mean, of course, was 268. And now you might be thinking, well, 15 days is our standard deviation, so 266 is only 2 away, so that might be really close. But remember, it gets cut by the square root of your sample size. So the new mean, or our sampling, or sorry, our new standard deviation, our sampling standard deviation, would be this old one, 15, divided by the square root of 64. So that makes it a lot smaller. That makes it just under 2. So this 266 is about 1 standard deviation away, so it's really closer to that. And we're looking for the area in between. So as usual, we need a z-score, but we need our new z-score formula. So let's remind ourselves what that one looks like. That's similar to the old one, so it's x bar minus mu over standard deviation divided by the square root of n. So we have that extra part there. So we can plug all of this in. So this would, for the z-score for 266, plug that in there, 268, 15, and square root of 64. That would give you the z-score for 266. The z-score for 268 is just 0, because that's still the mean. Even in the sampling distribution, the mean stays the same. So it'll be whatever that z-score is up to this mean. You can do the normal CDF for that. So in this one, you get B. It's about a 36% chance that their pregnancies are, or the average of their pregnancies is in that range. Next one is similar. We have 36 men, so once again, we'll have to use this formula for the z-score. We want the probability that their mean height is greater than 72.5. We could draw a picture there. The mean was 71.5. And so 72.5, the standard deviation is 2.1 for a single man. But for 36, the standard deviation would cut that by square root of that, which is 6. Cuts it to about a 1/3 of an inch. So this is a full inch away. So that's actually pretty far out there in the sampling distribution. And we want the probability that it's greater than that. So we're looking for this tail area here. Again, I'll go ahead and actually do the plugging in. So you'd plug in the 72.5, subtract the 71.5, divide by standard deviation of 2.1, but you would first divide that by the square root of 36. And if you're putting this in the calculator all at once, you will need parentheses around both the top and the bottom for the calculator to do the correct order of operations. And so that gives you some z-score, and then you can do the normal CDF or look it up in your formula. Here's one that doesn't make sense at all. Remember, this is a probability that we're trying to find, so it can't be greater than 1. And again, judging by our picture, this should be a fairly small probability. So these two don't make any sense either. So the 0.002 is the only one that truly makes sense, but should also come out. If you look up the z-score, you should actually get the opposite one, which isn't listed here. So I guess I can figure it out. So 0.9979 is what you should get for the area to the left. So let's point that out here. So the area to the left, or probability that these 36 men have an average that's smaller than 72.5, is actually quite likely at a 99.8% chance. But the probability that they're bigger than that, all of them, or not all of them, but the average of all of them is a 0.2% chance, a very small chance of that happening. Okay, next we sort of put all this together, looking at the probability that a single cup of coffee versus a sample of 9 cups. So those probabilities will be different from each other. And the z-scores will be different in each case as well, because in one case we'll have to divide by the square root of 9 for the sample, and in the other case we use the original z-score formula without that square root of n. So let's draw a picture of what's going on here. So a mean of 12 ounces, standard deviation of 0.2 of an ounce, and we want the probability that it's less than 12.1. So it might be exaggerated in one of the cases. Probably not in the case where I have the sample of 9 cups. This is probably an accurate picture. But with the sample of just 1 cup, it's probably quite a bit closer to the 12. So in the first case, with the sample of 9 cups, you would use this formula up here with the square root of 9 to get your z-score. And for just the 1 cup, you use the version without the square root of n. So you get 2 different z-scores. You can look each of them up to find the area. Of course, one of them is going to be obviously bigger than the other. You should have ended up with B. So the 0.93, the 93% is like this picture that I have here with the sample of 9 cups. And then that drops when it's just 1 cup. So the probability that 1 cup is less than that is not as likely as all of them being less than that, or the average of all of them. Okay. Next, we want to compare scores on a test. We have, or on 2 different tests with 2 different averages and standard deviations. So this we actually did back in 2.5, really, but it is kind of connecting to the z-scores that we're using now versus the z-scores we used before. We use the z-scores to compare values that were otherwise not comparable because they're coming from 2 different worlds. Here we have 2 different tests. One has a mean score of 200 with a standard deviation of 21, and the other has a mean of 80 with a standard deviation of 8. So it'll be hard to compare which of these is better, this 220 versus this 90, because they're sort of coming from different worlds. So we just get a z-score for each. So the z-score for the 220, we plug in the 220 with its mean of 200 and its standard deviation of 21. And then we can do the same thing for the 90. Subtract its mean of 80 and divide by its mean of 8. Fortunately, I don't have the numbers here, but you just calculate each one of these, see which one is bigger. So it turns out that the score of 90 was a better score. Well, I guess I can do a little bit of, because this is what, 20 over 21, so that's less than 1. That's only just about 1 standard deviation above the mean, where this is 10 over 8. That's bigger than 1. So I guess I could have done this without a calculator. This one's definitely bigger than this one. So 90 is, or the score with 90 is better than the one with 220. Next, finding a z-score for a percentile. Here, the 80th percentile, or P80 as we had in the notes. So I'm going to use some of the space down here for it. So 80th percentile would be 80% to the left, so it'll be around here somewhere, where this area is 0.8. And so that's pretty straightforward. Just inverse norm of 0.8 would give you that z-score. And so that came out to be a 0.84. And the last one, also similar, but we're given the area to the right, so we need to convert to the area to the left. So that's 0.9989 is the area to the left, and so you can do inverse norm of that. Or in both of these cases, you could try and use the z-score formula, or z-score table backwards, but I prefer this. And that's what gave us, in this case, about a 3.07. But because of rounding, and if you tried to use the table, you would have found this number in there multiple times. Because of the rounding to 4 decimal places is just not enough to get an accurate z-score. So there was other answers here that I would have accepted as well.